Hi all, welcome you all to the YouTube channel of DCC NIT-A. This is Mayur and today I am going to discuss the problem E1 PermuTree, the AC version that came in Codeforces Round 890 Division 2. The problem states that we will be given a tree with n vertices and it is rooted at vertex 1. Now for some permutation A of length n, let F be the number of pair of vertices u, v such that this relation holds. That is, A is less than A of LC of u, v less than A of v, where LC is the lowest common ancestor. Now, I hope you all know what is a permutation. The definition is given here. Now, we are asked to find the maximum possible value of FA overall permutations A of length n. Now, I know this is kind of tricky one. This might not get totally clear. It might be a lot of confusing thing. So, we'll try to understand it with an example. So here this is a tree. It has five nodes, and this is the tree is like this. So let's assign means since this is a tree of five nodes, so we'll have a permutation of size five. This we have numbers from one to five, and we'll assign the numbers. Let's say in this order. Here this will have one, this will have two, this will have three, this will have four, and this will have five. Right? So now let's try to check what happens. So if I consider these two nodes, this one and this one, their LC is this, and here we can see one, it is less than two, it is less, which is less than four. So this is a valid pair. That is the pair two comma three, the nodes two comma three. This forms a valid pair. Now, if I check any other pair, let's say if I check this one, this node, and then this. So again, here we can see one, it is less than two, it is less, which is less than five, right? So 2 comma 4, the nodes 2 comma 4, this is also a valid pair, right? Now let's take a third pair. So here let's take it again, the node 4 and the node 5. Here you can see 3, this value 3, it is less than their LCM, which is 4, which is again less than this one 5. So the next pair is 4 comma 5. Now I guess you can find out another pair like this. The last pair is 2 comma 5. 2 comma 5, that is this one and this one, because here 1 it is less than 2, which is in turn less than 3, right? So in total we got 4 such pairs. And if you try any other arrangement of permutation, uh, let's say if I write here, if I write 2 here instead of 1 and 1 here instead of 2, you'll see that we are getting lesser number of pairs. At max, here, if you try out any permutation, we'll get 4 pairs at max. Now let's try it with a different example. Here we have another tree with 6 nodes. Now let's just write a permutation like 1, 2, 3, then 4, 5, and 6. So if I try to make the pairs, we can see that with this node, we have with node 2, we have node 3, right? Because 3 is less than 4, 4 is less than 5, these values. Then we have 2 with 6, correct? 2 is 3 is less than 4, 4 is less than 6. Their LC is 1, by the way. Then with 4, we have 4 comma 3, 4 comma 3, and 4 comma 6. Because both of their LCS is 1, and you can check out with the values. 1 is less than 4, which is less than 5, and 1 is less than 4, which is less than 6, like this. Now what are the other possible things? So now with 5, we have 5 comma 3, 5 comma 3, and 5 comma 6. I hope you now know the reasons. So in total, we got 6 pairs. If you try it, we don't find any pairs. You might think about these two nodes, 4 comma 5, but here the value is 1 here, and here it is 2, and here it is 3. And this is not a proper condition. This is invalid. This is wrong. So instead, if we just change the permutation, means if we just change the order of the permutation in a different way. So if I write it like 1, here 2, here 3, and then 4, 5, and 6. Now you have seen that I have changed these two values only. I've interchanged them. Now let's see how many pairs are there. So do we get all the previous pairs? Yes, we do. So here 2 and 3, this makes a pair, 2 comma 3, because 2 is less than 4, 4 is less than 5. Then 2 comma 6 makes a pair, 4 comma 3 makes a pair, 4 comma 6 makes a pair, 5 comma 3 makes a pair, 5 comma 6 makes a pair, and the new thing is this one, 4 and 5. This also makes a pair because their LCA is this one, and 1 is less than 2, which is again less than 3. So this again makes a pair, 4 comma 5, right? So this is the whole thing. I hope now you got the problem. So we need to arrange the permutation in such a way that we get maximum number of pairs as possible. And our target is to get the maximum number of such pairs. How many such pairs is possible? So for this, you have seen that by now you might get an intuition that if I write the middlemost number here like this, and if I write the smaller numbers in one side and the larger numbers in one side, then we'll get something like at let's say in the left side here we have three nodes. In the right side we have two nodes. So we will get at least 3 into 2 pairs, right? As you've seen in this example, for means where one is the LCA, correct? Now coming for this smaller one, here the smaller one was like 2, then 4, then 5. Here I've assigned the permutation values like 1, 2, 2, and 3. So again here in the left side there is one node, in the right side there is one node. So if this is the LCA, so we again get 1 into 1, that is 1 again. So one more pair. So 3 into 6, 3 into 2 are less 6 pairs, and here 1 pair. 6 plus 1, 7 pairs. So that is like a basic intuition that we might get. Like let's say we have a random tree where we have 8 nodes in the left side, let's say 5 nodes in the right side, right? Right. So these are the number of nodes, I must say, number of nodes, not the actual node value. So 8 is the number of nodes, 5 is the number of nodes. Let's say there are, means this also is subtree like that. So 8 nodes here and 5 nodes here also, like this. So if there are 8 nodes in the left side, 5 nodes in the right side, now I can arrange the numbers in such a way that this, the value in the permutation here for this always lies in the middle. Means let's say I have how many nodes are there in total? 8 plus 5 plus 1. So in total 14 nodes are there. So what I will do, I will assign 1 to 8, the values 1 to 8 in the permutation in the left side, the value 10 to 14 in the right side, and 9 here. I'll assign 9 here, the middle one. That is according to the count of the nodes. So in that way, all the nodes in the left side is smaller than 9. All the nodes in the right side are greater than 9, right? So I can take an intersection for all of this. Like I can intersect all the 8 nodes with 5 nodes. That is, I will get 8 into 5 in total 40 pairs. Correct? That is the thing. Again, you can use the same logic here in this subtree. Again, you can use the same logic in this subtree like that, and you can go on recursively, and you will find the count. That is the maximum possible count. Now, this looks pretty simple for a binary tree, right? Here I am considering a binary tree. Let's say means if I have not make if it was like a binary tree only. So this was pretty simple. I would just make the LCA node as the middle one in every call, in every recursive call, and we would have gotten the answer pretty easily. But What if this is not a binary tree and it is an analytic tree? That is it can have any number of nodes. For example, let's take a smaller tree at first. One, then two, three, and four. So this is a tree and it has three children. So if I assign the permutation values like one here, two here, three here, and four here. So these two makes a pair because one is less than two, two is less than three. So we get one pair, two, three. Now again, these two also makes a pair. So two comma four because one is less than two, two is less than four. But these two doesn't make a pair because three is not less than two, right? So we get two pairs. Now, if I take another example, let's say one, two, three, four, and five. And if I assign the values like one, two, three, four, five, so we get the pairs as two comma three, then two comma four, two comma five. That's it, right? We don't get any other pair. So three is the answer for this. But if I just change the permutation, since I order the permutation, like let's first draw the tree again. One, two, three, four, and five. And if I just make the permutation like one, two, here now three, then four and five. So we get it like the pairs are one comma four, one comma five, two comma four, and two comma five. So in total we got four pairs. That is the thing. That is, we try to make it as middle as possible. Means let's say now let's again take another example. Here let's say this is the root node. Now this is the left side has a node which is again four children like this. So this is four children. Then again this is a node. It has let's say three children. And again here there is a node and it is again five children. Correct? So if I just write it in short, so I can write it as one. This left side has four children. This middle one has three children. This one has five children. Now, if I, what are the possible options? Let's say now I can assign 1 to 4 values here, um, 1 to 4 values here, then assign it value 5, then 6 to 8 here, and 9 to 13 here, since there are 13 nodes. So I've assigned the values like this. The values 1 to 4 for this part, 6 to 8 for this part, 9 to 13 for this part, and 5 here. So this is the combination. Now here, how many pairs will you get? Here we'll get here 4 into 3, that is 4 into 3, 12 pairs. Now again here for this one with this one 4 into 5, that is 20 pairs. Do we get any more thing? No, right? Because we can't combine these two because 5 is not in between them. 5 is smaller than 6 to 8 even. So here we get 32. Remember this. Now let's try another combination. So what we can do is uh, instead, if I assign 1 to 4 here like this, then 5 to 7 here, then 8 here, and then 9 to 13 in the right side, 8 here. So how many pairs do we get? Again, 4 into 5, 20. Then 3 into 5, that is 15. Do we get any more? No, right? Because I can club this two because 8 is larger than 5 to 7 even. So we get 35, right? So now this is a better option. So does this give you another intuition like depending on the here we have 4, we have 3 and we have 5. So what we need to do is like we need to partition them in such a way like we need to divide them into two groups, right? One group will be smaller than the parent one group will be larger than the parent one. So if I just write this, this is a smaller side, this is the larger side, right? So we need to divide the children into two parts. One is a smaller part, one is a larger part, such that we get the maximum possible product value. That is, we'll multiply each number of each side, or like the sum. That is, we are adding them 7 into 5. So we'll multiply 7 into 5. That is, we want to get the maximum possible value for left into right. We need to divide the two parts into two partitions. Means we need to partition them into two parts, left and right, such that we get the maximum possible value for left and right. And this happens when left and right are like near about equal. Like I guess you have done a problem in DP, which is like divide partition an array into two parts, such that the difference between these two partitions is minimal. So that is the thing. We have to divide the whole means 435 or like whatever. Let's say we have it. We have a thing like uh, let's say we have it. The children are in the order like 2, 3, 7, 6, 5, 14, 21. So the parent has 7 children, which in turn has this many children, right? So 2, 3, 7, 6, 5, 14, 21. So we need to partition these children into two hubs such that their multiplication, that is left into right, is maximum. And when do we achieve that? When both of the sides are kind of comparable. That is, the difference between them is minimal. Let's say, let me show you an example. If suppose the total sum is 20 in one case, or let's say 24, 24, right? Now, the numbers are like, what can be the numbers? 2, 2, then, um, not 2, 2, let's say, okay, let's take a smaller example, it will be easier. Let's say 6, the sum is 6, and the numbers are like 1, 2, 3, correct? Now, one way is like you can multiply 1 with 5, that is 1 into 5, which gives me 5. Another way is like you can multiply 3 into 3, 3 into 3, which gives me 9. Now, that is what we are doing here. We are dividing the the whole thing into two hubs, and both the hubs are comparable. 3 and 3 are comparable. Their difference is minimal. Whereas 1 and 5, this is a higher difference, correct? Even if I take here means 2 in one side, let's say 2, and the other side is 3 and 1, so 4. This is again 8, which is again not the best one. So the thing is, we need to divide the children into two hubs such that their left and right are comparable. And this is a common standard DP problem. That is, we are minimizing the difference between them. So now let's take a look at the code and see the implementation to understand it further. So initially we have taken n, the input, and then we have made the edge tree in the form of adjacency matrix. Then I have initialized the result and I call the function and then printed the result. Now let's see what happens inside the function. Here, every time we also need the count of children, right? So this function basically returns the count of children for this tree. So we are first going through each of the adjacent nodes for this, and we are also adding children here. That is, this is a pretty standard one for finding the count of children in a subtree, and we are also pushing it in a vector because we are making this vector, right? Here we are making this vector. This all these are the number of children in a subtree. So we're pushing it in this vector so that we can further use it. Now, the next thing is we need to partition the vector into two parts such that we get the best results. So again, I'm calling a helper function for this so that I can partition it into two parts and get the best results among them. And last time returning children plus one for the children one. Here you can also see that I'm calling recursively for each of the subtrees. So first we'll call for each of the subtrees and then process for its parent group. Now let's see what happens in the helper function. So in the helper function, I've initialized a DP with of size n cross total plus one. That is, total plus one is the number of children. Here you've seen the number of children. That is the maximum possible sum of this array. Here, this whole thing, this what is the maximum sum or what is the sum for this? This is equal to the total number of children in the whole thing, right? So both of them are equal. So I purged children here as total. So this is the DP one, and then I have done the DP using recursion and memoization. Here, this is like the pretty standard DP form. The first thing is like I can take the first option I have is like, what if I take the current number, that is the current group of children. It will give me one possible option and the other is not take. I will take this and I will go to next. And lastly, I will and in the end, what is the base case? The base case is when it is equal to v dot size, will return total minus sum into sum. So what is basically happening here? We are like finding all the possible sum values, all the possible values for sum. Let's say I have an array of like this. So what are the possible values? Like I can have a sum is 2, where I don't take all this. I don't take all this. Now I can also have sum is 2 and 3. There is 5, and I don't consider this one. I can have sum is 2, 3, and 6. That is 6 plus 3 is 9. 9 plus 2 is 11. I'm not considering 7. I'm not considering this one. So like all the variable combinations or like variable various values for sum, I'm getting them, and at last the two partitions are like in one side I'm getting the sum, the other side is total minus sum. So these are like the two partitions, and I'm multiplying them, and we're taking the maximum for them, whichever is maximum. Yeah, whichever is maximum. And lastly, I'm returning that. So for every node, I am just getting all of its children's conditions or like the values or the number of children it has. Then I'm applying this whole thing. Sorry, this whole helper part. For each of the node, first I am getting the children, count of children it has, and then I'm partitioning them into two parts such that they are comparable and I get the multiplication value is maximum, the product is maximum using this DP1. And lastly, I'm just adding them, all of them to result here. So that is the whole thing. This thing might be pretty confusing if you don't know the DP problem regarding this, which is to partition an array into two parts such that their difference is minimal. I will again attach the link for the DP problem in the description as well. Now, if you have any doubts regarding this problem, you can mention it in the comment section. I'll try to explain or solve it as much as possible. Thank you.